Hello mathematicians, we're now going to take a look at volumes of solids of revolution. Solids of revolution are the shapes which are formed when we rotate a curve around either axis. So we're going to use our integration techniques to find those volumes. So when we rotate a curve around either x or y and get our solid of revolution, what is it that we're actually doing? Well, we're taking a two-dimensional shape and turning it into a three-dimensional shape. So if we have a look at that first on GeoGebra. So this is what we mean. We're taking the function, in this case here, square root of x, which we know is the top half of a parabola. So here's our curve, top half of a parabola. We're going to take that curve and rotate it around the x-axis. And we're just going to look at the segment of the curve between 1 and 12. Over here on the right hand side is the shape that we get when we do that rotation. If I change the limits of integration, we can see that the shape changes. And if I just change the view over here slightly, we can see that sort of funnel shape that we get is the volume, or is the solid of rotation around the x-axis. So our task is to be able to find the volume of that shape. Just before we leave that, here is one more example. So this is the curve y equals x, our straight line y equals x. We have this shape here which we're rotating around, which we're rotating around the axis, and this is the shape that we form down here. So again, you can see that that is some sort of a funnel shape. So our technique for finding the volume of these solids of revolution is a technique known as volumes by slicing. So what we do is to take our 3D shape and slice it into thin cylinders perpendicular to the axis around which the curve is being rotated. So here, for example, is our curve y equals root x. We're going to rotate that around the axis, and we know what that three-dimensional shape will look like. So we take a thin slice of the area under the curve, and when we rotate that thin slice, then we get this disc. And the disc has a thickness of dx, so that's the thickness in the direction of the axis that we're rotating around, and it has a radius which is equal to the y value, so that's f of x. So then, when we add up the total volume of all of these little cylindrical slices, that gives us the total volume of the three-dimensional shape. So that's the basis of integration. So if we look at these problems here, in our first one, y equals root x, we're just going to find the volume of the shape that we get when we rotate this curve around the x-axis, and we're interested in the section of the curve between 2 and 4. So our formula is that each little slice is a disc which has an area pi times r, which is root x squared, and the thickness of that little disc is 2x. So what we're really doing is finding the volumes of little cylinders and adding them up. We can think of this formula overall, though, as just being pi times f of x all squared dx. So as we apply that formula then, after this first step, it's all straight sailing. So we simply evaluate that term, which is x, don't lose the pi, just there, do our integration, which gives us that, put in our limits of integration, and when we do that, we get 6 pi cubic units. Generally, we don't evaluate the pi, we just leave it as is, because that then gives us the exact volume of the shape. Now, if we look at our next example here, you can imagine the shape that we get when we rotate about the axis, which is a bit of a clue. So we can go through it the long way. We can say that it's pi times f of x, so square root of 4 minus x squared, all squared, which gives us this to integrate. We can go through, we can do the integration. Plug in our limits of integration and we get our final answer of 16 pi on 3 units cubed. However, we could have also just thought about shape when it's rotated around the axis, so that what we see is that we actually have a hemisphere when we rotate that shape. And it's easy enough to find the volume of the hemisphere using our formula for the volume of a sphere to get our same result. Likewise, we can see our next example. The area that we're going to rotate is a semicircle, so that should simply give us a sphere. And it's quicker to do the volume of the sphere formula than to use the integration technique. Now, just as we could rotate a shape around the x-axis, we can do the same with rotating a shape around the y-axis. And in this case, our integral becomes that the volume of the shape is pi outside of the integral from the y value a to the y value b, f of y all squared dy, where f of y is just x as the subject of our equation. So if we look at our first example here, we're going to rotate this curve, x equals root y, around the axis between y equals 0 and y equals 1. So we've got pi times the integral of between the two y values of our curve with x as a subject, squared dy. Now we need all of this in, so you really need to understand the significance of every part of that setup. Once we've done that, then there's nothing new. We simply carry out the squaring process, we do the integration, and we get our answer and leave it in terms of pi. For our next example, we can see that we've got a hemisphere which we would be rotating, a semicircle which will give us a sphere when we rotate it, so we could use our volume of a sphere formula. For the one after that, with this particular curve, we're going to be rotating something unusual around the y-axis. So our volume is pi times the integral from -1 to 1. We could have probably also done twice 0 to 1 of our curve squared dy, the axis we're rotating it around. And when we go ahead and do that, first of all we square it, then we do our integration, we plug in our limits, and being careful, especially with negatives, we get 16 pi on 3 cubic units. Now we can even find the volume when we rotate the region between two curves. And in that case, it's useful to think of it as being the outer volume having the inner volume cut away from it. So that gives us the structure of our integrals. We find the outer volume and we subtract the inner volume. So in this particular problem here, we've got this parabola meeting this line at these points, so they're supplied, we don't have to solve simultaneously. Sketch the diagram, so that looks like this, and then find the volume of the solid generated when this region in here is rotated first of all about the x-axis and then about the y-axis. So around the x-axis, our outer shape is the one formed by rotating the line, and our inner shape is the one formed by rotating the parabola. So it's the y equals x squared and then the y equals x squared, which go into our expression for volume. Then we go ahead, we can take pi out as a common factor, and it becomes x squared minus x to the fourth. Do our integration and plug in our limits, and we get this as the volume when rotated around the x-axis. Now, it's a bit of a challenge imagining that shape, but it helps if you try it. If we take that shape and rotate it around the y-axis, then the similar technique is that we've got pi times the integral from 0 to 1, and this time, when we're going around the y-axis, the outer shape, or the bigger volume if you like, is formed by the parabola. So if we take y equals x squared and we make x the subject, we get root y, and we're going to square that root y to get y down here. The innermost shape is the line y equals x, or therefore x equals y. We're going to square that, and our integral will become this. We go ahead and do our integration, plug in our limits, and we get pi on 6 cubic units as our result. So this has been a very powerful set of techniques, but they're only small additions or extensions to what we already know. So in terms of putting together your ideas here, for this section about volumes of solids formed by rotation around the axis, what are the key ideas that you need to get your head around so that you could tackle any volume question?